Now I want to extend our discussion of limits from last time to an important and highly related term called continuity. In math, the term continuous has much the same meaning as it has in everyday use, and that's a good thing for us. And what I'm going to say about that to make that bridge is that when I say that a function is continuous at a point x equals c, what I mean by that is there's no gap in the graph at f equals c. And that's a very intuitive idea. For example, in the graph I've drawn here, around that point c, the curve is unbroken. It has no holes, it has no jumps, any kind of gaps. It's just a continuous curve in the everyday sense of the word. So again, to just emphasize this, in the intuitive idea of continuity, I will say the best way in my mind to visualize it is that if you take a pencil and you can sketch out, trace the entire curve without lifting your pencil, then you can say that that graph is continuous. For example, here, I can sketch that entire curve without lifting my pencil from the paper. So in this sense, with the arrows on both sides indicating it continues in that pattern, I could say that this graph is continuous from minus infinity to infinity. In other words, it's continuous everywhere. If you have to, at any point though, lift your pencil to complete the graph, if you must, then that's a point of discontinuity. For example, this strange looking beast, if you're sketching it, you have to raise your pencil at the point where x is equal to 3 to get around that hole. And then again, you have to raise your pencil to get from the left side of the vertical asymptote at 7 to the right side of the graph, which goes past 7. So there would be 2 points of discontinuity, one at x equal to 3 and one at x equal to 7. Think of the number line, the x-axis, as a rope. If you have two discontinuities, it's like you've cut the rope twice. And if you cut a rope twice, you end up with 3 pieces. So the first piece, that represents everything from minus infinity all the way to your first point of discontinuity at 3, but not including 3. And then you have a continuous piece between 3 and 7. And finally, once you get past 7, from 7 to infinity, you have a continuous piece. So those 2 points of discontinuity break the graph into 3 pieces, each of which is continuous. Does that make sense? Think about it visually. I think is the most intuitive way of all of thinking about it. Now, I'm going to give some formal definitions, but I want to downplay the formality and think about the intuitive nature of it. But just suppose we've got a function over some interval from a to b. And on that interval, we have a point C1 where there's a hole in the graph. There's just a hole. At C2, we have a point where, well, one piece has a hole, but basically what you really notice is there's a gap. There's a gap between the left piece and the middle piece. And then the third one is also a hole, so there's a hole in the graph. It's a little different than the first one because the hole, below the hole, you have a dot at that point C sub 3, f of C sub 3. And that just simply means that if you plugged C sub 3 into the function, you would get the y value for whatever that c value would come out to be. Whereas in the first one, C1, there just simply is no y value. But in any case, the main point is not those details that I've just enumerated there. The big idea is anytime you have a hole or a gap, you have a point of discontinuity. That's the important point. So in the first case, there just is no value at C sub 1. That causes a hole, that causes a point of discontinuity. The second one, the basic thing is there's a gap. If you take the limit from the left-hand limit, and the limit from the right-hand limit, they come out to do different things. That means the limit itself does not exist. And if you know the limit doesn't exist, you can be certain there's going to be a point of discontinuity. And finally, the third one has similarities to the first one. Basically, you have a hole in the graph. That assures you of having a discontinuity. But the function does have a value at c sub 3. For our purposes of just looking at the intervals of continuity for the pieces, the distinction doesn't matter much. But for other things later it might. So in any case, you look for gaps or holes to break your graph into pieces, each of which is continuous in a certain interval. Think about it graphically if possible. Now I'm going to put up a formal definition of continuity. I really don't think you'll need it. It's mostly there for reference, so I'm not going to go through it in detail, but I will say that when you look at the continuity of a function at a point, it really has three conditions to be satisfied. When you plug c into the function, you have to get an answer. And you can see if you have a hole in the graph, you're not going to get an answer. You've got to have a limit as x approaches that number c. In other words, left-hand and right-hand limits have to equal each other. And the two answers from 1 and 2 have to be equal to each other. This is the answer from step 1. This is the answer from step 2. They have to be the same. If one comes out to be 5 and the other comes out to be 7, then the limit does not equal the function value, and you still would not have continuity. So although I'm not going to break that down any further, you basically see the same things we saw earlier in the graphs. The points of discontinuity come when you have holes and gaps. That's really all that's saying there. Two really important things, though, are the following. A polynomial function, and we've talked about this in the context of a limit, a polynomial is a very well-behaved function. It has no gaps or holes. So earlier we talked about the fact that to calculate the limit as x approaches value for a polynomial, all you have to do is plug the number in. Similarly, for continuity, you don't have to worry about any gaps or holes. So a polynomial function is going to be continuous from minus infinity to infinity. Whenever you see a polynomial function, you never have to worry about having to break it into pieces to get continuity within each piece. A rational function, in other words, ratio means fraction. It's a fraction of two polynomials. Anything that's in the domain of the rational function is going to be an interval of continuity. But whenever you see a rational function and something causes you to divide by 0, that's going to put in a vertical asymptote or a hole in some cases, and that's going to cause a point of discontinuity. So a rational function is a little more complicated than a polynomial function, because a polynomial function you never have to worry about discontinuity. A rational function, the only points of discontinuity are places that cause you to divide by 0. And we're going to see that through some examples. For example, f of x equals x squared minus 2x plus 3. Based on what I just said a minute ago, you don't have to overanalyze it. You have to realize that's a polynomial function, and you have to realize that a polynomial function is continuous at every real number. So there are no points of discontinuity, and if you wanted to say where it was continuous, you could say that it's continuous spell continuous from minus infinity to infinity. There aren't any points of discontinuity. There's another polynomial function. So again, it's a polynomial function. Once you know it's a polynomial function, it's going to be continuous at every real number, so you could say the same thing about it, that it's continuous from minus infinity to infinity. So that would have a similar way of writing it if you wanted to. Again, another polynomial. Once you know it's a polynomial, you know that a polynomial function will be continuous at every real number. So again, you can say it's going to be continuous from minus infinity to infinity. So all three of those. Once you know it's a polynomial, the answer is the same. The function will be continuous everywhere, minus infinity to infinity. So the simplest case is if you have a polynomial, you don't have to worry about any discontinuity at all. You don't have to have a graph in order to look at the continuity. But if you did have the graph, you could see that those are the three graphs of those three functions. You could sketch each of them without putting your pencil off the paper. So it's nice to see the graph, but you don't need the graph to see that it's continuous. As long as you know it's polynomial, you know it's continuous everywhere. Now, although a polynomial function has no points of discontinuity, rational functions are going to have points of discontinuity wherever the denominator is equal to 0, because you can't divide by 0. Everywhere else, the rational function will be continuous. In other words, a rational function is continuous on its domain, but values that aren't in its domain are points of discontinuity. Here's another example. What if I take that first function I listed just a second ago, f of x equals 1 over x? That's probably the simplest rational function you could possibly think of, just the number 1 over x. Think about it, a polynomial function has no undefined values, but here, 0 is not in the domain of that function. You cannot divide by 0. That means 0 is a point of discontinuity. So if you think about a number line and putting that point of discontinuity on the number line, x can never be anything that causes division by 0. That breaks the number line. It's like taking scissors and cutting the real number line as if it were a rope into two pieces. So there's continuity from minus infinity to 0, and then there's continuity from 0 to infinity. But there is a point of discontinuity at x equals 0. And that 0 comes from looking at what causes division by 0. There's the graph. As I've said, having the graph is kind of nice, but you don't have to have the graph to answer the question. How about this one? F of x equals another rational function, x squared minus 1 over x minus 1. Again, the only place you can have a discontinuity, a point of discontinuity, is when the denominator is equal to 0. So what value of x, value or values, causes division by 0? If you look at it, you can see that it's 1. If you try to plug a 1 in, you're going to get division by 0. That means 1 is a point of discontinuity, so the function is continuous to the left of that from minus infinity to 1, but it's also continuous to the right from 1 to infinity. And there's a point of discontinuity where you get the division by 0, and that is at x equal 1. Again, having the graph is nice, but you don't have to have the graph to sketch it. And if you're wondering why that function didn't have a vertical asymptote, it just had a removable discontinuity, that happens whenever you get one of those type 0 over 0s that we talked about in the context of limits. If you try to plug a 1 in for x here and here, you end up with 0 over 0. And it's the same thing with the limit. That's what I call a yellow flag that tells you could go back and simplify, in fact, factor and simplify and remove that discontinuity. So if you factored x squared minus 1 is x plus 1 times x minus 1, and what you see happening is the x minus 1s will divide out, and you just get f of x is equal to x plus 1 as long as x is not equal to that value that causes division by 0, which is 1. So what you end up with is just a hole at 1 instead of a vertical asymptote. So that's the visual difference, and it's important in other contexts, but in terms of answering the question about where it's continuous, it really doesn't matter. What matters is this 1 comes from getting a 0 in the denominator. That's the important thing. How about this one? F of x equals 1 over x squared plus 1. And this one's a little bit different because you're looking at where the denominator is equal to 0, but the denominator is x squared plus 1. But x squared plus 1, think about it. When you square a number, even if it were negative, when you squared it, it wouldn't be negative anymore. 0 squared is 0, 1 squared is 1, 5 squared is 5, negative 1 squared is 1, negative 5 squared is 25. No matter what you do, you're not going to get a negative number when you square any real number, and when you add 1 to it, it's certainly going to be positive. So there's no way the denominator will ever be 0 on that one. So it's continuous everywhere. You can't find a place where the denominator is 0, so there is no point of discontinuity. Again, you don't have to have the graph in order to answer that question, but if you do have the graph, you can see that you could sketch the entire graph without lifting your pencil from the paper. So it's continuous on the entire real number line, minus infinity to infinity. I'm not going to make a big deal about this, but whenever you have just a hole in the graph, just a plain simple hole, that's called a removable discontinuity. Anything else is called non-removable. For instance, here, that graph we had earlier, that's a removable discontinuity. And I guess the way to think about it is it's so easy to get rid of it by just filling in the hole. It wouldn't even be a discontinuity anymore if you just put a dot where that hole was. In that sense, it's easily removable. An asymptote is not. That's called a non-removable discontinuity. So if you get something like f of x equal 1 over x, there's no way you can just fill in a dot and get rid of the discontinuity. There's just a jump, a gap or a jump between the negative values of x and the positive values of x. So that discontinuity is called non-removable. So if it's just one single point missing that's causing the entire discontinuity, that's removable. Otherwise, it's called non-removable. Again, I'm going to put these definitions up here, and as much as anything else is for reference. If you get in the middle of a homework problem and sort of lose your train of thought, forget what you were doing, or get confused, you can go back here and look at the actual definition. So that's the definition of continuity on a closed interval. I'm not going to say anything about that right now. I'm just leaving it there for reference purposes more than anything else. But it does exist if you have a problem where reading through that carefully would help you get rid of some confusion. But don't think you're going to need it for the homework problems we'll be dealing with. I think our intuition is going to get us through on that. So let's go to example. Suppose we take this function defined by a rule. We've dealt with these before in the context of limits, but now let's look at it in context of continuity. G is 5 minus x as long as x is between negative 1 and 2, including negative 1 and 2. But g of x is x squared minus 1 if you get bigger than 2 and up to and including 3. So we're looking at the continuity. Now what I would say about this is the pieces are continuous because they're polynomials. The top piece is just 5 minus x. That's a simple polynomial. So we know from our earlier discussion that all polynomial functions are continuous, no gaps. And the second one, the bottom one, is x squared minus 1. Again, that's a simple polynomial. So the individual pieces are not going to have any discontinuities. The only real question is, are there going to be any discontinuities overall going all the way from minus 1 to 3? Now notice there aren't any gaps. There aren't any gaps at all between the interval from minus 1 to 3. You can go all the way from minus 1 to 3 and you won't miss a value of x, and that's because the equality for 2, if you're exactly 2, you go into the top half. You have to be bigger than 2 to go to the bottom half. So there's no gap in the whole interval from minus 1 to 3, and each piece in and of itself is continuous. So the only thing you really have to check then is when x is exactly equal to 2 on both pieces. The bottom one, of course, is in the sense of a limit, really, but in terms of practicality, all you have to do when you see a function defined by more than one rule where there's no gap in the domain at all you have to do is take the place where the rule changes. Notice the rule changes at 2. 2 is where you go from the top to the bottom. So you just have to check 2 in the top one. 5 minus 2 is 3, and then you check 2 in the bottom one. And that's 2 squared minus 1 is 3. And if those two values are the same, then you can say that the function is continuous over the entire closed interval there. Had one answer come out to be 3 and the other one negative 2, then it would not be continuous. There would be a gap there. So because each of these pieces in and of themselves are polynomials, we don't have to worry about discontinuities within there. The only place a discontinuity could happen is where the rule changes, and that's at 2. So after you see this, you really know that all you have to really do is check the place where the rule changes and see if the top and the bottom piece give you the same answer or not. That's what the graph looks like, but it doesn't really matter in terms of what we're doing. This is actually a part of a parabola, but it's very steep, so that really is more parabolic, but you get the idea. Now let's end with an application. A mail service first-class mail rate is 34 cents for the first ounce and 16 cents for each additional ounce or fraction of an ounce, up to 3.5 ounces. First of all, let's graph that function. I'm going to call the function C, I guess, for cost. So I'll create a horizontal axis with the weights, and the vertical axis is going to be the cost of mailing the item. Up to 3.5 ounces, so along the horizontal axis, I'll number 1, 2, 3, but instead of going all the way to 4, it just says up to 3.5 ounces, so I'll just go to 3.5. On the C-axis, though, what happens? Well, you have to read the problem to see those are the actual cost of mailing something, first class. Well, what it says is up until you get to an ounce, you're at 34 cents. So anything up to an ounce is going to cost the same, 34 cents. From nothing, from no weight at all to an ounce. It's hard to imagine something weighing nothing, but the point is the mail service is not going to mail anything for free. Everything you put in there is going to be 34 cents at least. And then when you get to an ounce, it's still 34 cents. But as soon as you tip over to above an ounce, it goes up another 16 cents. So if you're looking to see what happens if you've got something a little bit bigger than an ounce all the way to 2, you have to add 16 to 34 and see that the items that weigh more than an ounce up to and including 2 ounces are going to cost 50 cents to mail. So the next mark on the C-axis is 50 cents, and that's going to be valid all the way up to and including 2 ounces. Notice that I put an open circle on that segment over 1 because the dot below it takes care of the case of exactly 1. When you get exactly 1, you're at 34 cents, not 50 cents. And then you keep that pattern as you go. As long as you're over 2 but less than or equal to 3, you're going to pay another 16 cents, which is 66 cents to mail that item. So that's going to be a line segment that as long as you're bigger than 2, up to and including 3 ounces, you'll be paying 66 cents. And finally, you might think, well, I'll go from 3 to 4, but it said to stop at 3.5. So I add another 16 cents, which makes it 82 cents. But I don't run it all the way to 4 because it said to stop at 3.5. Technically, it doesn't say what happens at 3.6 or 3.7. It said to stop at 3.5. But anything that weighed 3.5 or 3.1, 3.3 ounces would be 82 cents to send. So there's the graph. Then find the x values where there's a discontinuity. I guess I don't need the word on. Find the x values where there is a discontinuity. Well, the discontinuity is where the gaps or the jumps are, and that's easy enough to see from the graph. There's a jump at 1, there's a jump at 2, and there's a jump at 3. So the points of discontinuity are at 1, 2, and 3 on the x-axis. And finally, find the cost of mailing a 1.7 ounce first-class letter. With the graph, that's simple. You just find 1.7 on the x-axis, the horizontal axis, cross-reference it up, and you find out that it costs 50 cents to mail a first-class letter. There are some other examples that are possible when you do the assignments, but the idea is if you understand the concepts, you can figure out the details to solve variations on these applications. So that's sort of an example of one that you might see. Practice a lot. The more you practice, the more this is going to be second nature. My contention is a lot of this is very intuitive, and the more you practice, the more your intuition gets honed, and the better off you will be.